finite element analysis category or subcategory. And then you have heat transfer, you have electromechanical fields, you have solid mechanics, you have soil mechanics, you have acoustics, biomechanics, various other aspects of FEA which can be applied in various other fields as well. So this is what your generalized FEA basically deals with. And then you have multi-body dynamics, or in other words called MBD, something that most of you all might have heard of. So multi-body dynamics basically deals with kinematics and dynamics of your systems and subsystems. So if you are having a robotic arm, which is supposed to have 2 degrees of motion, let's say it's supposed to move in x-axis and y-axis. So is it actually moving in x-axis and y-axis without having any disturbances, without having any intrusions in between? So these kind of understandings of how the product is going to move under a set of given motions, or under a set of given, let's say, conditions. Is it satisfying what is actually required, or is there any issues that you might face given the design? So this is what your multi-body dynamics will deal with. There are various categorizations, or rather various breaking of the domains again. So you have something called machinery, which specifically deals with machining tools or machining objects. And then you have car. This domain specifically deals with the automotive sector, and most specifically deals with the four-wheelers. And then you have aircraft. Aircraft specifically again deals only with aircraft. You have motorcycle, which deals with two-wheelers or motorcycles. Anybody deals with biomechanics as to how a given joint is replaced, and if it is replaced, is it performing properly or not? So all of this is dealt with multi-body dynamics. And then we have computational fluid dynamics, which basically deals with how a fluid flows and what type of flow is there, how is that affecting your overall design, is there something that needs to be changed, is it just the design that needs to be changed, or is there some major changes that needs to be done? So all of this is basically studied in your computational fluid dynamics. So I'll quickly introduce you to finite element analysis, which is the major part that we'll be discussing in today's session. So as I told earlier on, from the early 19th century, from 1930s onwards, a lot of development was basically being done. What was development being done? It was basically a simple software or a simple programming language which is used using direct equations to solve a set of problems, which was handy for most of the scientists or most of the people who were working with various structures. So they developed finite element methodology then, and then they started using various equations and tried various forms of equations, and they were able to sustain a stable platform where they could perform certain set of where they could perform certain set of problems and arrive at some solutions. So that is where finite element analysis or finite element method was developed. In very simple terms, finite element method is nothing but breaking down your engineering problem into small pieces, solving for each one of that piece using elements and nodes, which are representations that we will be talking about when we get into the more advanced classes. And then after you solve for each one of these small parts, you put them together in a meaningful way. Then accumulate or conglomerate everything together and form the holistic solution. So you have the big problem, you break it down into smaller problems, you solve these smaller problems, then assemble them together to understand how the entire product or entire part will basically perform under the given set of situations. So this is what finite element method basically deals with, right? So why do we have to use finite element methods? Why can't we use analytical methods? Analytical methods, as I told earlier on, is used for simple problems like a cantilever beam or a simply supported beam. It's all well and good, but as we talk about realistic problems are not so straightforward. The realistic problems basically will have so many set of complications which will come into picture as and when you start solving the problems, or as and when you start solving the boundary condition related problems. So it could be related to your geometry complications, sorry, complex geometries, or it could be related with the type of loadings that the structure has to take in, or the type of complexities which could be with respect to the material. So all of these various parts can become complex, and that is where FEM methodology is very suitable, or is very useful for engineer to basically arrive at a solution at a faster pace. Okay. If you look at the realistic problem, so this is just an exaggeration of a real-time problem, and how that real-time problem is represented in your finite element method, or in a CAE environment. Okay, so here you have a simple cantilever beam, but if you look at the beam itself, the beam has two different portions. One is a tapered cross section, the other one is a continuous cross section. So you have to represent these types of variations as well within the CAE platform. So there are various ways, various methodologies to represent these types of shapes, or irregular shapes, or complex shapes, or whatever you want to introduce into the platform. Right. So all of these have certain set of rules, a certain set of boundaries are there. Within these boundaries, you can make various kinds of changes and represent the real-time problem into the virtual platform. Okay. So here you have, as I mentioned, two parts. One is tapered beam, the other one is uniform cross section. But then again, the tapered beam could be of a different material. Then you have the uniform cross section, which could be of a different material. So because these two are different materials, how will they perform? Which one would take larger loads? All of this can be tested and are tested and verified even before you can actually get into a prototyping. So if you look at the fundamentals, so this is the basic fundamental, or this is the basic of how a CAE, or how a FEM program basically runs. You have a set of equations. So the equation could be, for example, in this case, we are looking at equation of equilibrium, which is F is equals to K into X, or otherwise represented with a D, which is nothing but displacement. So this equation where force is equals to K, which is nothing but your stiffness, which is your stiffness, and then X, which is your displacement, is taken into a matrix form. So matrix form will have your forces, your stiffnesses, and your displacements put in proper places. And then you will have something called knowns and unknowns. So if you know what your force is and you want to understand what the displacement is, so your force is known, and what is unknown is your displacement, which will be calculated. So depending on the boundary condition, for example, if let's say for a given set of conditions, your F3 is 0. So if your F3 is 0, how will that affect your set of problems? If let's say one of the degrees of freedom is fixed, so how will that affect your problem? So all of these kind of variations and iterations can be basically performed thanks to this form of matrix form, or thanks to all of these form of FEM methodology, which is now established and scrutinized, and also now being commercialized with minimalistic glitches and problems, right? So this is how equation is basically solved in your finite element analysis, or a finite element platform. Okay. Then, if you look at various technologies which are available in the market, so you have various technologies which are being provided by various vendors or various suppliers. So most of you all might have heard of Dassault Systems. You might have heard of ESI Group, Siemens, Ansys, or Comsol, or Altair Engineering. So various other engineering suppliers are also present. These are few of the ones which are most widely used and mostly talked about in the industry. So you have Dassault systems, you have ESI, you have SimScale, you have Siemens. I'm sure most of you all would have heard or at least worked on one or two of these softwares. And so in these various softwares, there are various applications. They can be used in multiple locations. So each set of supplier has something specific to offer. So if you look at Dassault systems, they specifically offer non-linearity as their major, I would say, home ground, or non-linearity as their specialization. If you look at ESI group specifically deals with injection molding and those kind of softwares. And then you have Siemens, which deals specifically with the PLM software, that is your product lifecycle management. Then you have ANSYS, which deals with static, dynamics, non-linear and multiple things. Similarly, you have MSC software, which again has a set of products that can be catered to. So these are all the various suppliers which are present. To specifically talk about MSC software in a little bit, because we are going to touch upon Nastran and Patran as a major software that we will be looking at. So MSC Software basically was founded in 1963 by two different people, McNeil and Schwendler. So these two people basically formed a group and they started developing, and they started forming these programs into packages and trying to give various people, trying to collect their feedbacks and developed on the programs further and further, and that is how the company started. So the company developed its first structural analysis software called SATSAM, which is basically an abbreviation, structural analysis by digital simulation of analog methods. So this is back in 1963. This is right after NASA had given out, or rather, NASA was actually looking for specific applications which could solve or which would give solutions for the problems that they were facing. So in 1965, MSC, was basically able to grab a contract through NASA, where they were able to commercialize the software or the program that they had worked on, and NASA was their direct utilizer or direct benefactor of this software. And from there onwards, they started changing their name, or started giving proper names for their softwares. The first software that they came up with was the solver, which is Nastran. The full form or the abbreviation for Nastran is nothing but NASA Structural Analysis Tool. Okay, so that is what it basically stands for. And then, if you look at various other tools which was developed from way back in 1965 to today's scenario, these are all the various tools that they have developed so far. Patran and Nastran were the first tools that they developed. Nastran was the solver part. Patran was basically acquired later on, which was utilized as a pre and post processor. Okay, and then they later on again acquired Adams, which deals with multi-body dynamics. Mark, which specifically deals with nonlinear problems. I'm not sure how many of you are aware of it, but Abacus was initially a part of MSC products. They sometime in I think 1990s they split away from MSC and they started working by themselves as Simulia products. So, so Mark basically deals with nonlinearity. Diatran specifically deals with your what we call impact simulations, or in other words, called explicit simulations, which deals with damage in small amounts of times. And then you have fatigue tools, which basically help you to understand what would be the lifetime of the product under a given set of situations or under a given set of conditions. And Sim Expert is another pre and post, which is used for various solvers. Then you have Sim Manager, which is partially like a PLM platform, but very small in its application that it can handle various databases and what you would say, your files basically. So it will reorganize and have everything in place. It's not full-fledged like your PLM tools, but a portion of it is basically handled with Sim Manager. Easy5 is specifically used for what you would call is the proper terminology would be um, what is it called? Um, Control simulations, control systems. Okay, so if let's say, for example, you have a landing gear. So if the landing gear has to operate, certain amount of pressure needs to be applied for the liquid, so that the landing gear will open up, right? And then you have the wings, the active parts of the wings, which has to basically flip up or flip down. So all of this is basically handled using hydraulics or electronic systems. Today it's electronic system, but if you look at landing gear, it is still the hydraulic system which is used. So how is that control system basically being performed? Is the flow or is the pressure being exerted properly? Is there any issues? So all of this control system is basically studied with EZ5. Sinda deals with specific types of thermal problems, which are represented in the form of resistors and capacitors, to simplify the thermal problems in a application form. And then Actron basically deals with your sound and how the sounds basically propagate in different mediums. So all of this is handled with Actron, right? So we'll quickly go through the important products, which is Patran and Nastran. As I told earlier on, Patran is the pre and post for most of the solvers. Uh, in any um, in any given situation, you would have heard of pre-post, which is something like a separate entity from the solver. MSC has this. Then I think Abacus also, to a certain extent, can perform both integrate in an integrated form as well as in a separated form. And then OptiStruct, which is a specific career path, you have to wait patiently, no, gather up all the years, and then you'll be able to move up the ladder as and when you become more and more experienced within the organization. Okay, so your other aspect of promotions also depends on the flexibility that you have and the capability that you have in terms of leadership skills or in terms of being able to motivate other people, being able to perform tasks by yourself. So all of these will basically be able to give you a promotion as and when the industry set their time period. Usually it is once in a year. Some organizations do it half yearly or quarter yearly as well. So it depends on the organization level. Then you have tier one suppliers. Tier one or tier two suppliers are specifically working on certain set of subsystems or certain set of systems. Something like, let's say, hydraulic systems, or let's say suspensions, or let's say tires. So these are all tire suppliers or tier one or tier two suppliers, where they have worked on those subsystems. They have extensive knowledge on those subsystems that they have been working on. So if you want to get into tier one suppliers, the easiest way would be to get through your college, what do you call them, placements. So if you are able to perform well in the college placements, then you can get yourself or land yourself in a good job. That is one way of doing it. The other way of doing it is by being able to perform certain set of PCs or projects which are specifically related to certain subsystems. So by doing these sort of projects or doing these sort of PCs work, uh, PCs does not necessarily mean just doing PCs work. You also have to submit a paper, and the paper has to be published somewhere. So as long as you meet these requirements, you'll be able to land an interview. And again, after you land an interview, you should be able to crack the interview and then join it. Okay. So that is how the tier one suppliers basically, go around. And then if you look at the advantages of for tier one suppliers, their technical knowledge on the given subsystems or given system is excellent. They have gathered, years and years of experience on that particular subsystem, or a bunch of those subsystems or variations of those subsystems. So even if you ask OEMs, they would also not be in a position to give you the details of certain things. But tier one suppliers can tell you what kind of variations can bring in what kind of changes in the behavior of the part. So that is the level of knowledge that you gain in the tier one suppliers. So this is the major takeaway that you will get if you work in a tier one supplier. Now talking about OEMs, original equipment manufacturers. OEMs basically have various departments within them. Just because you're working for OEM does not necessarily mean you are in a good position, right? So as I mentioned, they have various departments. So they have something like support department. They have R&D departments. Um, what do you call uh, again, depending on your domain, they will break it down again. So they will have optimization department. They will have um, thermal department. They'll have CFD departments, etc., etc. And if you join, how do you basically join them? One is the most common way, which is again similar to your tier one suppliers. They have college placements that is happening. So if you're able to crack an interview there, well and good, because you will be able to join OEM directly, which is a huge boost to your resume. Anytime after a certain set of time you spend there, you'll be able to move up in the career in a better way. The important perspective that you have to keep in mind is here, unlike tier one suppliers, you have to gather the knowledge of the product. So it's not just FEA, not just CATIA, not just design. You have to gather the knowledge of the entire product, how the product is built, what are the various no, bottlenecks which are present, how they are broken through that. All of this is something that you have to go through. That is when you basically have a lot of advantage over the rest of the types of works that you will get into. Uh, so that is about your OEM or original equipment manufacturers. Um, the other important thing is you need to work in different departments as well, like I mentioned. So that is the unique and the most important takeaway that you will get through a OEM. And then you have consultants. Consultant basically is something that is specifically looking for um, hands that have worked or have experience, and not something that is easy for a fresher to get into. So consultants will basically look out for experienced engineers who have worked in multiple fields. They don't just look at one field. They want people who have worked in multiple fields. So if you look at the nature of the job of the consultants, they can work anywhere between a small subsystem that has to be worked from scratch all the way to building the entire product itself. So the consultants are something like the third party organizations which basically form a team with let's say startup company, help them, guide them, or they will also be able to take up projects internally and help them build the project from scratch itself. So that is the kind of works that the consultants do, and they generally prefer experienced hands, somebody who's got experience with multiple levels and in multiple domains as well. Here, the advantage is once you get into a consultant or consultancy, or work with a consultant, the advantage is that the probability of you becoming an entrepreneur becomes higher. Unlike in most of the other scenarios that we have seen, consultants or working in a consultancy gives you that kind of a confidence, because you will not just be working with one product or with one kind of um, part. You will be working with multiple domains, multiple parts, multiple assemblies, multiple products itself. So that is the kind of flexibility, or that is the kind of takeaway that you have with consultants. So this is all the various things that I wanted to kind of discuss about in today's meeting, but I think I may have extended the time beyond what is given to me. I do apologize for extending my time. Uh, Without further ado, if you have any questions, please shoot the questions.
Thank you, sir, for the informative session. So can we move ahead for the Q&A part? Hello, sir. Can you hear me?
Yes, please. You
Yeah,
can go ahead.
yeah, sure. So participants, we have been receiving a lot of your questions and you're open to send us further questions too. So to start with the first question of the day, how concurrent engineering plays a role in product development?
Right. So concurrent engineering and okay. So if you're talking about the type of engineering processes that are being in place, there are two types of process. One is the conventional process. The other one is the concurrent engineering process. Conventional process is where everything is fixed. Your process is fixed. So let's say if you're doing a fastener, or if you're doing a bolt, or if you're manufacturing nuts and bolts. So there you don't basically need any kind of innovations, or you don't need too much of changes with your product. The products remain the same. Whether you use a M8 bolt or M10 bolt depends on the type of application it is used. So in these kind of applications, or in these kinds of products that you are developing, you only need a conventional setup. You don't need a concurrent setup. I tell you what concurrent setup is. So concurrent setup basically deals with having various teams. What are these various teams? You will have a design team, you will have a simulation team, you will have a testing team, you will have a manufacturing team, you will have production team, you will have a quality team. So all of these teams working in tandem, helping you to realize a product. That is a concurrent engineering team where everybody has set of targets, and each targets are being reached parallelly. So this kind of a setup is what we call as a concurrent engineering setup. If you look at most of the OEM setups today, most of them are concurrent engineering setups. If you look at fasteners, or if you look at nuts and bolts manufacturers, they are conventional setters or conventional followers of manufacturing. So this is the major difference between having a conventional type of engineering system and a what we call a concurrent type of engineering system. I hope that would give you that answers your question.